The Hairy Ball Theorem states that for any vector field on S2, it must vanish somewhere. To prove this, we must focus on two things. We'll focus on the non-vanishing vector field and the winding number. But first, what is S2? S2 is topological notation for the set of points such that mod P is equal to 1, such that xy is equal to P. No, it's xyz. xyz is P, sorry. So that's saying that any P is a coordinate in R3, and we take P, find the modulus, which the mod of P is the root of x squared plus y squared plus z squared. So that's the Euclidean distance. And it's saying that all the points around this, well, the origin really, must be one away in order to be an S2. So we end up with a figure that looks a lot like this, which is a sphere. So you have your center there, you have a radius, and that would be of 1. And we're looking at the vector fields over this sphere, which we call S2. What's a winding number? Well, a winding number is a way of denoting how many times a function goes around a certain point. So if we took this function here, which is x squared plus y squared is 1, the unit circle, we would say around the point 0, 0, it has a winding number of 1. If, however, we took a different graph, something like this, we could say that it, put it a bit more like this to make it a bit more obvious, then it would go around the origin once, twice. So that would have a winding number of 2. And then you can carry on adding different spheres, cycles, until you have whatever winding number you want. But the funny thing about this is, because we're doing topology, we can take any sort of squiggle that we want, and we say, well, this one here also has a winding number of 2 because it does one cycle around the origin. So there's something called an invariance of the winding number. So we can take any squiggle or any cycle, and we can say that this is the same as our circle. That's called the invariance, which will be used later. I noticed something called the rules of topology. The rules of topology say that everything is basically like plasticine. So if we had any sort of shape like this in 3D space, we can then say we're going to use the rules of topology to bend it and fiddle with it until it comes back into a sphere. So any sort of solid shape that we have in 3 dimensions, in topology, that is homeomorphic, which means the same as a sphere, because you can just meld it, and that's not very good for the sphere, but you can meld it and mold it until you get into a spherical shape, and you can carry on doing that until you get into a proper sphere. To construct our non-vanishing vector field, let us consider the S2 again and a mapping. We'll call this mapping V, and V will go from S2 to R3. So it'll go from our sphere, that one or that one, that was a hairy ball. Take this sphere here, we can take any point on that sphere and we will map that into Cartesian space. X, Y, Z. That's what V does. So we can take a point P, B of P, and that will be a point on our sphere, and we just map that to, say, that point there in Cartesian space. So what happens if we dot this, dot product, or sometimes people call it the inner product. No, you can't see that. Or VP, P, the inner product between two vectors. Because of course, P is a vector, and so will VP. So we can take a dot, that makes sense. What would happen if we did this? Well, we're going to say that's 0, because it's taking a point in 3D space, and it's been changed into R3 such that it's now perpendicular to your original vector. For our Hairy Ball theorem to be able to be proved, we shall say that P is always non-zero, and preferably positive. But that's not a thing that needs to be worried about that much, as you'll see later in the proof. So we've got P that's non-negative, and when we dot it with the mapping version of VP, we'll get 0. And so our vanishing vector field is a field in 3 space or S2 where there is no vectors that have a 0 length. So at no point during that sphere there is a vanishing vector. Let us start to prove Hairy Ball theorem. So we're going to take a couple of mappings. One's going to be called P, one's going to be called E, and another's going to be called N. First, let's look at P. P will be the mapping of a theta t into a 1 minus t squared cos t, or cos theta, sorry, then 1 minus t squared sine theta, and then a t, and our n is going to be theta t again. N, or north, will be negative t cos theta, negative t sine theta, root 1 minus t squared. And finally, E, we've got in our space. Ooh, may not be. We're doing it a bit dicey. E, again, theta t is going to be our negative sine theta, our cos theta, and our naught. This E is obvious, it's just going to be a sphere in 2-dimensional space, but placed in a 3D plane. So it'll be in the z equals 0 plane. Then P will be a circle again, but it will be upright on the y-axis, and north will be a half sphere. I think I've got I'll put up the diagrams that I drew about now. Now we have our mappings, we question what the domain of these mappings are. Given that theta is an angle, we know that theta will be from 0 to pi. But what about t? Well, we have a sphere of radius 1, and the most obvious thing to go for is negative 1, 1, because that'll cover both sides of the radius, and it will cover every angle around. Let's take a partial derivative of E with respect to theta. We can see that the partial derivative of E with respect to theta be negative cosine theta. Then it would be negative sine theta, and then 0. And if we evaluate that at t is 1, or theta, yeah, t is 1, there's no t's there, so that's fine. What if we evaluate n at t is 1? We get negative cos theta, negative sine theta, naught. So we can say that the partial derivative of e with respect to theta is equal to n at t is 1. From this, well, not from this, but we also can say that the basis of this vector space will be En. Again, looking back at the figures, that's pretty obvious to see because the E is the circle, which is something like this, and N is a circle that, well, this lies in the Z plane, this lies in ZY really, and that lies in the XY plane. So then you can take the basis, take any point on here and any point on there, and that'll form basis of the sphere that lies within all the plane. So because we know it's the basis, and we know that this, the partial derivative of E with respect to theta is n, we can say that this rotates with positive direction and increasing theta as you get to the North Pole, and when we get to the South Pole, it goes in a negative direction with increasing theta. Now we can assume that V is a non-vanishing continuous tangent vector field on S2. Remember that S2 is our sphere. This is drawn awfully. And a tangent vector field will mean that we take all of the tangents of this sphere all around the sphere, turning it into, if we take this to be our hairy ball and all the bits of rubber being our tangent vector field, well, we can already see it's exhibiting Hairy Ball theorem, but imagine this is our vector field. And we're going to assume, for the sake of a contradiction, that our vector field is non-vanishing. So now we can take the vector field, which we shall call V, to have unit length. This is very important. It makes calculations easier, and we'll define something called another vector called u, and that is v dot p. So you dot every vector on this vector field with the p, which is this. I'm going to call that u, and from this u we shall create a new mapping. This mapping is called h, and it's going to be in two space. So h will be u dot e and u dot n. That's our new mapping. Nothing complicated, just the two dot products or inner products. Because h is in 2 dimensions, we can take, again, u dot e and u dot n. Surely h will map 0 to pi, because we're using these. Oh, they're gone over there now, but we're using the same thing, and we're going to Cartesian product that with negative 1, 1. So you take all the bits in here. Cartesian product, if you had two sets, A cross B, where A is AB and B is CD, you just iterate through. So A cross B, which would be AC, AD, then BC, then BD, just iterate through and with different bits. So you do that between 0 and 2 pi, where 0 and 2 pi are included, and -1, 1 and -1 and 1 are included. And this here will, I'll try again, maps to, let's change to green. That will map to our S1, which is a new sphere we haven't come across, which is a subset of R2 minus 0, 0. That's a set minor symbol, so it's all the coordinates with 2 numbers in, apart from the origin, which is 0, 0. S1 is defined similarly to S2. It's mod P is equal to 1 such that xy is an element of R2. It's what I got confused with S1. It's confusing because there's two coordinates here. It's in 2 space, but it's denoted by 1 topology. We can say that U theta 1 is equal to V 0, 0, 1 due to the way it's defined. And from this, we can then say that it rotates in a negative direction relative to our positive rotating basis, because we're in the Z plane at the North Pole. And then we can say the curve has a winding number at theta 1, using h theta 1 of, where is -1, where w is the winding number of a certain curve. And you can have a look at the winding number of h theta -1. Oh, that's 1. Oh, do you remember what I said earlier about the invariance of winding numbers? That a winding number should stay the same even if you change the variables in the equation. A homotopy is when you take a function and you're able to use the rules of topology on that function, i.e. not making any holes, turn it into another function of that kind. So you take a family of solutions, and a homotopy is melding one of the solutions into the other using the rules of topology. So we could take this blue curve and we could move that up, 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 move it down, move it down, move it down, producing the green curve. Our H mapping is a homotopy because we can meld spheres and circles into each circle because we're not creating any more holes. So if we had a sphere here, we can we can meld it into a circle. Now, there's a badly made circle. I haven't made any holes, so that's still allowed. And I can turn that circle back into a sphere. A badly made sphere, but still a sphere. This means our invariance is valid on H. So because of that, and we have 2 different winding numbers, because we have the winding of H theta 1 was -1, and the winding of H theta -1 is 1. Yeah. So this means that V cannot be a vanishing vector field, because that's the only assumption that we made. So this proves Hairy Ball Theorem, that on any vector field in S2, it must vanish somewhere. So this vector field must vanish. Going into real world applications, surely the Earth is homeomorphic to a sphere. So we can take Hairy Ball Theorem and we can place it onto a sphere. So we can place it onto the Earth. So if this was the Earth, if we had a vector field over the Earth, like the wind, we could say that in exactly 2 places, there will be no wind on Earth at all times. And we can say that because the wind is a vector field. Wind has magnitude and direction, and it occurs in more than one place. So we can look at the vector field that is wind over the Earth, and we can say that in 2 places there will never be wind if there's wind everywhere else in the world. Those 2 places are not the same place. They can change, but it's still amazing to say that on the Earth you cannot have wind everywhere. There must be 2 points where there is no wind. Because wind can be described as a system of differential equations, we can say that in general with differential equations there must be 2 points on a sphere where there are almost poles, where the differential equation where it vanishes basically. This is sometimes used in partial differential equations on a sphere to help solve a system of equations, because you can take the points where you think it could be 0 and plug that in and try and resolve the differential equation down into a simpler form. We followed the proof of Eugene Curtin, which you can see I've nicely annotated. There are many proofs of Hairy Ball Theorem out there. I just picked this one because I liked it and it was easy to explain. There's another proof that I've been looking at by Marai Espriano and Robert Guy. This is a more complex proof, and that's the reason I didn't go for it. But the front here has some nice information on led to the Hairy Ball Theorem being discovered. And one of the most interesting points on here is that this is a generalization of the Poincare-Hopf theorem.